Hi there, and on this very captivating video I will be speaking about the diffraction from basic aperture shapes. So basically what I will be doing here is that I will apply the just introduced Fraunhofer diffraction integral into a scenarios of three different aperture shapes. So mainly a single slit, a rectangle, and a circular aperture. And I will calculate how light is being diffracted caused by these kind of apertures, and basically what are their irradiance distributions of diffracted light. So this is what I will be doing. So essentially I will be applying what we have already learned, but now we will actually take use of actual given specific aperture functions instead of the general picture. So we will consider a few scenarios, and we will start by a single narrow slit as our first aperture function, and this has been explained in the figure. So we are considering a slit that extends into infinity along the y direction, but now only in the x direction the slit is open from points of or planes from -a/2 to plane of a/2. So this is where the slit is open. Light can propagate when it's inside the slit, and otherwise we expect and assume that our aperture is entirely opaque to light, so that no light propagates through the screen. Since the slit doesn't look spherically symmetric or rotationally symmetric, we choose the differential surface element ds that we will be integrating over in our Fraunhofer diffraction integral to be dx and dy. And in addition, the nice thing here is that our problem is actually separable, so that our aperture function, that's in principle a function of x and y coordinates, we can separate this function to be only of a function of x variable multiplied with a function of a y variable, and this really helps our integrals. So this we really can use, and this is a common property, or not maybe very a common property with functions, but whenever you can take use of this separability of a function as a property, then it really helps out performing the integrals. And sometimes you can do this on a Cartesian basis, but sometimes you want to go into a different coordinate system just to make your function to be separable over different integration variables, and then you can more easily perform the actual integrations. So this is what we have learned in many occasions already, and this is sometimes what we will continue applying in different problems at hand in physics. So we are also assuming that the incident field on the slit, the EA field, is a constant valued and of the order of unity, equal to unity. So EA equals unity. This simplifies our treatment. And now we can really start calculating the actual integrals, and we start with the y direction. So we have the total field now along the y direction. This is the contribution caused by light being possibly diffracted along this y direction. So like I said, the problem is separable. So we can first consider what happens along this direction for diffraction, and then we can consider what happens next along the x direction. And the first integral, the diffraction integral, is that we have the common multiplier, the phase term, and then we integrate. And now since our slit extends from -infinity along the y direction into infinity, this is where the integration limits are. And now we have the integration kernel that is left. So no x coordinates there, only the y coordinates here. And now we know that what is the outcome of this kind of integral. We extend that to infinity. So this is essentially a delta function, where the delta function is picking out only this ky per capital R parameter there. So this is the outcome of my first integral, simply put. So essentially I'm just taking use of the known property that this kind of plane wave integral over -infinity to infinity essentially is a delta function. And of course, it's not really a function, but rather a distribution. So be careful when you talk about mathematicians doing this kind of integrals. So maybe you should be more careful. But we physicists, usually we are not careful folks, we're happy folks, and we like to do things and get things done. So I do not worry too much about the fact that it's not actually a function, but rather a distribution. So don't worry about that yourself too much neither too. So what this result tells us, that now looking at the observation point y, capital Y, we only see that, or kind of physical interpretation of this, that only a single ray originating from a single one direction, and this direction k prime would basically be this, what is inside the argument of the Dirac delta function, so ky per r, and this can be disguised into a to be a k times sine theta y, so that we can now see more easily that this really is just one single ray of light coming or associated with a one direction of propagation. So this is what we have here. And now this diffraction of light along this y direction, we only are being affected by this kind of physical reality. So in fact, the delta function picks out a single ray and no other rays potentially blur the diffraction profile along the y direction, but rather it stays crisp and sharp when we are looking at things. So essentially, physically, this means that the light is not being diffracted along the y direction because the slit extends to infinity here. But of course, like soon we will look what happens when this integral is not from minus infinity to infinity, but rather is being restricted due to the fact that we actually in fact do have an aperture here. And we will soon discover what happens then. So now we can consider the integral along the x direction, and this is exactly the same kind of integral with the same assumptions, but now the integration limits do not go from minus infinity, but rather from minus a over 2 into not infinity, but a over 2. And now what we get out is that we can actually perform this integral, and what we get out is that we have this multiplier coming out from here, and then we have the minus r per ikx here, and then we perform the integrals. We place in the values of a over 2 and minus a over 2 in there to calculate the proper integral, and this is what we get out. And we can shuffle terms here so that we get a formula that we have 2 times the 2r divided by 2I times kxa. And then we have the exponents inside the parentheses again. So something looking like something sinusoidal. And here, this is why I wanted to change things so that I have 2i here, so that I can combine that with these two guys here, and I can even take the minus sign here inside the parentheses. So actually I have something that looks exactly like a sign here. The only trouble here is I have this kind of term here, but in fact, if we look things more carefully, I see that this is in fact the inverse of the argument that we have inside the exponents here. So this is actually not that bad at all. So we can really easily and nicely describe this result by just defining a new variable. So we can define a variable alpha to be kxa divided by 2r. And now we can interpret this as a normalized direction. So basically that would give us some kind of understanding that somehow different directions are being associated with the diffracted light. And this variable alpha, the nice thing about it is also that we can use that to simplify the resulting integral. So this is already what we have shown. And now this integral actually can be written very easily using the cardinal sign of this new variable alpha, which is essentially a normalized direction. So this is how things can be solved and simplified quite easily. So what we have here is that there is this. And I cannot avoid myself, but here now we can see more easily that if you would want to be more rigorous about the Dirac delta function, so instead of calculating integrals such as the integral in the previous slide, we would be more careful by just considering first an integral with these kind of limits, and we would be able to calculate that this would be the result. And then in fact, we would consider the limit of that kind of integral when we are extending the limits of integration towards the infinity. And then we would see that we would be approaching something that gets narrower and narrower and narrower. And ultimately that would resemble our delta function. But rather, of course, we would always need to be dealing with this limiting function, and we thus would not really call it a function, but rather it would be better said like a distribution. And of course, there is always the trouble that can we perform the limiting process, and this is the kind of trouble that many times us physicists do not want to go into that kind of level of sophistication with the mathematics. But rather, we are just happy in using delta functions as they have. But their properties, essentially, we would get also by performing this limiting action on this kind of integral. But more on this you can find, of course, from the internet. You can just Google Dirac delta function. I'm already sure that in the Wikipedia you get a lot of information already, and maybe distribution theory would be the next step. And from there, you would get a better understanding what I was trying to say here. Okay, so what we have now done is that we have solved the diffraction integral. So basically we know how the field looks like, and now we want to understand how the irradiance looks like along the x direction. So we can just take the square modulus of the fields, and then we get that the irradiance looks like some kind of a normalization factor. So irradiance at the zero location, and then we have the cardinal sign squared here. Essentially, this is what we get out. So this is how the irradiance This is how the irradiance distribution looks like along the x-coordinate. And along the y direction, no diffraction of light actually took place. So light just continues to propagate as it is when it's seeing that kind of slit, when we're looking at the kind of performance or behavior of light along the y direction. And now the cardinal sign as a function of a, like we can see how that looks like in case you're not yet familiar with that. Like this is the kind of result, how the irradiance distribution looks like of this kind of single slit here. So essentially here, this width of the slit is causing a diffraction of light, and how the irradiance distribution looks like, it's basically proportional to the cardinal sign squared. So this kind of functional form it will have. So this is what happens essentially when we would be measuring the diffraction of light. And depending, there's an inverse proportionality here, so that if it would increase the width of my slit, then the distribution would get narrower. So in a way, physically, we could understand that less diffraction would take place. And if we make the slit to be narrower, then the cardinal sign function actually gets broader. So there is this kind of inverse proportionality between these two variables. So this is how my irradiance distribution looks like, and basically it forms a different distribution, so it affects the irradiance of the nearby observation points. So basically it tells me that when I'm looking at a kind of a given observation point, due to the diffraction, that point doesn't look like a point light anymore, but rather it has become a blurred, obscured spot. Another way would be to think of the situation by just thinking a light as rays of light. So originally I would come with a single ray of light into my slit, but because the slit is so narrow, like a white light starts behaving like a wave-like quantity, so that this single ray picture doesn't work out anymore, but rather I should understand things by waves. And now effectively what happens is that instead of a single ray propagating through the slit, I'm now getting actually many rays propagating in slightly different directions. So that would be my blurriness, the cardinal sign type of functional form for a diffraction here. So instead of like a single ray of light, now I'm actually having light diffracted, and there I can see that the many different directions of light actually are now rays heading in many different directions are now taking place due to the fact that I have a slit that causes diffraction. So light diffracts along the x direction. That's in a nutshell what I was trying to say. And diffraction becomes stronger when the slit width A is being reduced. So I think I'm being sloppy here. A and x actually are not, well, in a way they are so-called conjugate variables, but I would be better in saying that the actual small x coordinate here would be the variable. But in a way, at least, these two can be understood that if A gets smaller, then x gets larger. If A gets larger, then x gets smaller. So basically there's this inverse proportionality associated with essentially the transformation properties, like integral transform relation between these two parameters. So basically the Fourier transform connection. Now, let's consider the second type of an aperture. So we can really generalize our slit into a case of a rectangular aperture, and this is now highlighted in the figure. So now instead of a slit extending all the way down to infinity along the y direction, I'm also having a perturbance here, an opaque matter here, so that the light doesn't anymore propagate when I'm actually in a coordinate along the y direction that is larger than b over 2, and the same thing along minus direction, so negative direction of y, so minus b over 2. So essentially I have a rectangular function as my aperture function as shown in that figure. So height of the aperture is b, and again we can define a helping variable beta similar to the alpha variable, but now instead of x coordinates and a coordinate, I'm actually defining that with respect to the capital Y and B parameter, but otherwise it's exactly the same kind of new normalizing variable as alpha. And now I can simply calculate the irradiance of the observation point. I do not need to repeat the integral along the y direction because I already done it along the x direction. So what I get now, and this applies because the function, the aperture function was separable, so that I have my original irradiance distribution associated with the 0, 0 location, and then I have the cardinal size squared of alpha variable, and then I have the cardinal sign squared of a beta variable. And what that essentially means physically is that now light starts diffracting along both directions. So this is now the kind of difference that we have from the slit case. And this is nice, like we are able to generalize things in one step at a time. So we first understood a single slit, and now we can, with a simple extension of the math, we can already understand more complicated apertures such as this rectangle. And this is also a way more realistic scenario, so that it really doesn't extend to infinity. And now we're considering the circular slit. So this would be our third aperture, and that has been shown in the A figure. So it has the radius of A as the parameter, size parameter, and the diameter, of course, D would be 2 times A. And now this is a not smart thing to solve anymore in the Cartesian coordinate system, but rather it has a circular symmetry, rotational symmetry. So it's better to go into the it's better to go into the cylindrical coordinates. So this is what we will do, of course, and now subsequently the math that we do becomes slightly different. And now we will take the distance of the observation point from the origin to be q. So this is my new variable of interest, and we do not show the actual like a integral. How do we do that? But rather we take use of the known Fourier transform properties. So essentially our aperture can be written that it's a circular function, so circ function, and this we can place into the Fourier transform, and we can really just take use of the known properties of Fourier transforms and the known Fourier transforms to calculate how the diffraction profile would look like. And now I can write right away the irradiance pattern. So I will calculate or have a lookup table and use that to solve the integral for the field. And then I take the modulo square of that field and I get the irradiance distribution as a function of my q distance here. Again, I have my normalizing factor, so the original irradiance at the observation point of x0 and y0. And then here I have something that doesn't look very beautiful in first light, but when we look at it more carefully, it's actually not that bad. So now what I have inside the square is that I have 2 times a j function, and this j function is also known as a Bessel function. And these kind of functions quite quickly and many times they arise when I'm doing things on a kind of a cylindrical coordinate system, so that that's where we end up having these kind of Bessel functions. So essentially also when I would be solving differential equations in cylindrical coordinate systems quite easily, I would be ending up with Bessel functions, so that they actually are quite often encountered in physics. So this is how things look like, and in here in the B figure I have plotted how this normalized Bessel function looks like. So essentially look here inside the argument of the Bessel function of the first kind. That's why I have the one here. The argument is the same on the denominator. So essentially I can plot this guy here like this, and this is what I get out as a function of the normalized coordinate u here. So this is how it seems to be behaving. And here, this is still the not squared variable, but when I'm taking the squared, I'm actually getting the irradiance. So of course, I do not go into minus values here, but rather I will be getting a more wiggly line shape here. And then here I'm plotting how things look like in the x and y coordinates, so that how we can see that how this diffraction pattern has a rotational symmetry. So this is how it looks like. Basically like an airy pattern. That's also the very familiar name with this kind of distribution. So this is the diffraction integral, the irradiance distribution as a function of q, and the q is essentially the distance at the observation plane from the origo or the x0 and y equals 0 case, and this is how things look like. And now the thing here is that the central part of the diffraction pattern, it tends to 0 at a location where the KAQ divided by R is roughly 3.83. So essentially this is the location, and this is where the central part first of the diffraction pattern goes to 0. So most of the light is actually inside this value of 3.83, and only tiny portion of light actually is being in here. So this is how things look like. And this allows us to estimate the effect of the wavelength, that the matters on the size of diffraction patterns, or whether or not we can easily see diffraction patterns being forming. So that this is actually quite nice in terms of getting a better rule of thumb to understand when diffraction actually is a phenomena that may take place. So we have K times A times Q divided by R on the other side. So essentially this is what we have. We can equate that the K is equal to 2 pi divided by lambda. So we are left with the A times Q divided by R. And then we say that, okay, when this is at first 0, then we have roughly the value of 3.83 for this variable here. So essentially we know that this is when we are at this location. And now we can shuffle things around, and then we could, for example, estimate how the wavelength, when we would be changing the wavelength, how we would see things, how it affects the diffraction of light. So for example, how we would be able to either make the distribution narrower or broader when we change our incident wavelength. And of course, we can see from here that we have the Q parameter here. Or let's see. Okay, if we, for example, have the A parameter here and the lambda parameter here, if we increase the aperture size, then we will make this narrower, so that basically then we can see that the inverse would be true, so that when we increase the lambda, the distribution should become narrower and so forth. So we can already try to understand the system and the physics of the system by just looking at a simple equation. And finally, of course, we can solve the equation with respect to the coordinate q, the previous equation, and then we can estimate things maybe even more easily, so that we have 3.83 divided by pi times lambda times capital R divided by 2a, the radius of our aperture, and this is roughly 1.22 times lambda times R divided by d. And similarly, this function, we can understand that with respect to the propagation angle or diffraction angle, so the sine of theta r, that is basically defined as the q over r. This is approximately 1.22 times lambda divided by d. For small angles, of course, sine of theta is approximately the theta itself. So we could even understand that by changing the size of my aperture or changing the wavelength, I'm changing essentially how much light is being diffracted. So how quickly the ray of light is being diverging, because it's propagating through a small aperture. So this is some kind of good physical insights that we get out from here. For example, I could now just look into these equations, and I could, for example, change my wavelength, and if I would let this wavelength tend to 0, this would become smaller. So essentially it would mean that the diffraction angle becomes smaller, and that would mean that the light would be less diffracted. So in a way, another physical way would be of saying, and of course this is exactly the same thing we started with, that we assumed that the aperture, the size, is of the order of the wavelength. And when we are decreasing the wavelength while keeping the size of the aperture the same, of course that approximation assumption is not valid anymore, and thus we get less diffraction of light taking place. And this is also, for example, something that we will kind of use as a starting point in our final chapter regarding geometrical optics, where we are again going into the ray formalism of light and waves. And there we are starting our approach by just assuming that what would happen when we would have the wavelength of light tend to 0. And this is exactly that kind of things that we are seeing here in the mathematics, that when we let the wavelength go to 0, then we see that the kind of diffraction becomes smaller and smaller because of the kind of changes in the relative sizes of things. So that was my hopefully a useful prelude and motivation already for the chapter on geometrical optics. And hopefully I was able to point out that there's actually a lot of interconnections between the different topics in our different chapters, so that you would really benefit if you would also be going through the same material again the second time once you have gone through it the first time. So especially when you are recapping, reading again for the exam, I hope that you will get a better understanding of things, because then you're able to kind of already put things into a broader perspective and connect things with a different way than you may not yet be able to do. But now I'm at the end of my lecture. Now you know how 3 different shapes diffract light, and we have gone through the simple piece of mathematics. And of course, if you would need to go into more complicated shapes, either you can do integrals by brute force, but my recommendation is to be smart. Think, can you separate your function? Is it separable? And then, of course, please take use of the known properties of Fourier transforms and the known Fourier transforms, because most of the time you can really do the diffraction integrals by just looking at the known Fourier transforms. So that would be my take-home message of this lecture. I hope you enjoyed, and please enjoy the rest of your day. Thanks, and bye-bye.